Hi scholars, Ms. Perez here again with your new physics lesson. Today we are going to be talking about resonance and beats. Before we start our lesson, I will guide you through the materials that we'll need today and also the tabs that you have open. I am going to share my screen with you so we can do that. You should have your classwork document open from Google Classroom, right? And then you should have, and then the Simplicity of Science website open. Alrighty, I am going to share my PowerPoint so we can begin the lesson as well. Again, today, welcome to lesson Unit 5, Lesson 11b on resonance and beats. So today, you won't really need a calculator, but you'll need your notebook to take some notes, a pen and pencil, and then your classwork document, Google Classroom, and the Simplicity of Science website. So yesterday we saw how movements of an object while creating a sound can affect how we hear the sound. And we gave that phenomena the name of the Doppler effect. Today, we're going to look at other wave behaviors that affect how we hear a sound that's produced. So before we begin our lesson, have you ever seen a video of someone shattering a glass just by singing? Why do you think this happens? When I say go, you'll take the next minute to write your thoughts down in your notebook. Whenever you're ready to start again, you can hit play. Go. Welcome back. There's several things that you could have predicted here. One of the reasons you could have predicted that maybe singing at a really high pitch could have caused the glass to break, or by singing at a particular pitch, the glass might break, or maybe the pressure from the sound can cause the glass to break. So we are going to clarify your predictions by the end of the class. So I'm going to play a video that will introduce to us the two concepts for today. Okay, and we'll discuss what is on the video after we watch it. Great, so what did we just see? First of all, I just wanted to name that the things that they were hitting were called tuning forks. So tuning forks are two prong devices that are made out of steel that when you hit them, they vibrate at a specific pitch. So you can have different tuning forks of different pitches. So there are two phenomena that we observed here. The first one that we saw is called resonance. Because both tuning forks have the same frequency, when one is struck, it causes the other one to vibrate too. But then when the mass was added, it changed the frequency so it wouldn't resonate anymore. The second phenomena that we saw was beats, where two different frequencies are created close to each other, then they interfere and they create that effect of beats, where we heard that oscillating. So today you will complete a reading that will elucidate more on this topic, and then you're going to watch a few more clarifying videos that will help us better understand the phenomena of both resonance and beats. All right, so these are the 3 new vocabulary words that we're going to be adding to our notes today. We are going to be learning about force, vibration, resonance, and beats. You are going to find the definitions of these words in the reading. So you're going to read the article that's in your Google classwork, and you are going to annotate for the key points and definitions. And you make sure that you use the comment box feature on the right side of the document, just like you did yesterday with the reading on the Doppler effect. You will take the next 10 minutes to read and annotate this problem, and when I say press pause now, you'll start on that work. Whenever you're ready, just press play to join us again on the video. Press pause now. Great scholars, welcome back. So in your classwork document, there is an area. I'm going to show it to you, so make sure that it's clear. So the reading that you just did. And then below here, I'm going to show you 2 videos. You are going to type video notes here in the section where it says type here under video 1 on resonance. And then I'm going to show you a second video, and you're going to type any video notes that you're going to take here in this area under video 2 on beats. Okay, so I'm going to play just a short part of this whole clip. This video is around 10 minutes long. I'm only going to show you 3 minutes of it. The link for the whole video is posted on the Simplicity of Science website, so if you want to watch the whole thing, you can watch it there. So while I play the video, make sure to write down key points and anything you find interesting in the video in the classwork document. And just to frame, the video we're going to watch is this woman who's going to try to break the glass by singing.
He brought a wine glass to the space for me to try.
You're really looking to feel the vibration here.
Yeah, down here.
Yeah.
Okay.
And then just reduce the sweeps until you're feel like you're right on it. Yeah, we get it.
It's exhausting.
We get it.
Mike was telling me to try these sweeping noises up to the right pitch. Oh, I don't know.
Right, attempt 3.
Oh my gosh. I think this is one of the few cases in life where it's easier to learn a trick if you understand the physics. Also, I learned some major tips along the way, including the obvious ones like wear safety goggles and don't try this at home. The reason this is so challenging is that the note that you have to hold has to be the glass's exact resonant frequency. We'll get to resonant frequency, but first we need to think of the glass not as something that you drink out of, but as an oscillating system. An oscillating system is a system that goes back and forth, like a playground swing. I know that back and forth is a vague definition, but there are too many different types of oscillating systems to get more specific than that. Electrically and magnetically oscillating systems, economically oscillating systems, like an economy that goes up and down, yeah. But mechanically, these are all oscillating systems. So when you flick a wine glass, it vibrates back and forth, pushing the air, and that's what makes the ringing note that you hear. Now back to the playground swing. The swing is a totally overused analogy for explaining resonance, but it's just is so good. It's an oscillating system and it has a resonant frequency. You can describe resonant frequency two ways. One is that it's the frequency your swing will keep swinging at if you just let it go. In the wine glass, that frequency is the note it vibrates at if you flick it and let it ring. By the way, musical notes can always be described by their frequency or frequencies. Now, another way of describing resonant frequency is that if you drive your oscillating system at that frequency, it will have the maximum response in amplitude, meaning it'll have the maximum response in distance between the back and forth. So, if you push the swing at just the right moment, or in other words, you match its resonant frequency, the amplitude will increase. I know you've done this. And it'll increase more than if you pushed it at any other frequency. Now, the wine glass analog is that if you sing at the glass at its resonant frequency, your vocal cords are vibrating the air molecules that vibrate the glass and drive it at its resonant frequency. And then just like the swing will go higher and higher, the glass will vibrate or shake harder and harder. And if you shake something hard enough, it will eventually break. So that's why this is so tricky. You have to sing at the exact right frequency and hold it really loudly. I can't break this particular glass no matter how hard I try because I can't hold that note loud enough. So it helps to know physics and also to be able to match the right pitch. I should probably disclose that I did some musical theater and a cappella in my day, but hey, it helped with this. Goal accomplished, except the story is not finished.
Anyway, how cool was that? It was really, really awesome to see how just by creating, singing a particular pitch, she was able to break the glass. Unfortunately, we can't watch the whole video right now, but if you want to keep watching the rest of this video, the link for it is on the Simplicity Science website. So take the next 30 seconds to go back to your do now predictions and change and compare to what you saw in the video now, right? So as a summary, we saw that by creating a very specific pitch equal to the resonance frequency of the glass, then that's what causes the glass to break. Okay, when you're ready, you can hit pause now, correct your do now, and then press pause again so we can watch the next video. Okay, great, welcome back.
There was
okay, so now we're gonna watch this whole video. The previous one that we saw was on resonance, and this is going to show us about beats. Again, take notes in your classwork document under the video notes section.
It's for Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 117. It's on beats. Beats are changes in amplitude when you have two waves that have a frequency that's very close together. And you can actually play around with this if you're connected to the internet. And so I'll put a link to this down below. But if you go to this website right here and you launch it, what you can do is you can play a tone. And so what I'm going to do is play one that's at 440 hertz. I'm then going to launch another tab, and in that tab I'm going to briefly change what note I'm playing. So that's 440 hertz. That's also 440 hertz, but listen what happens when I change one of them. Those are beats. Now they're gone. Now as I go above it, you can hear the beats again. And as I bring them back to the same value, then it goes away. Now, when would this be useful? Well, let's say you're tuning your guitar. What you can do is tune one of the strings. So make sure you tune that to a tuner or a piano or something like that. Once you have that, then you can play another string. You have to move up on the fret, but play another string. And if it's close, you'll hear the beats. And if it's exactly the same, you can adjust the one, then the beats will go away. And then you can move on to the next string and the next string and the next string. And so waves, when they come together, will interact. And as they interact, they cause interference. Now that interference can be constructive, sometimes building up the wave or the summation of the waves, and sometimes it's destructive, it's tearing it down. But if those waves are very similar in frequency, what you get are these beats, and beats are going to be amplitude changes. In other words, the volume is going to go up and down and up and down and up and down due to this constructive and destructive interference. Now it's really easy to calculate the frequency of the beats. All you do is frequency of the beat equals the absolute value of the difference between the two frequencies. So if I know frequency 1 and 2, I simply subtract 1, and it's the value, absolute value of those. And so again, in review, if you don't know what constructive and destructive interference are, if we have two waves that are perfectly the same frequency and they're right next to each other, what we'll get is constructive interference. If they're out of phase with one another, we'll have destructive interference. But if the frequencies are slightly off, and if we look at this animation down here, these are frequencies that are close but not exactly the same. What you get is, as you have this constructive and destructive interference, you get the blue summation of those two waves, and you can see that we're seeing these changes in the amplitude. In other words, the amplitude is decreasing, then increasing, and then decreasing. Now, if I could make those frequencies exactly the same, then the beats are simply going to go away. How do you calculate it? Again, it's frequency 1 minus frequency 2, absolute value of. And let's do a sample of that. So I'm using Audacity. It's a little music software. And so what I'm going to do is I'm going to generate some tones. And so I'm going to generate a 440 hertz tone. So that'll be in one track. And then I'm going to add another track down here, and we're going to generate another tone. So we'll make this one slightly different. It's 440 hertz. Like that. Now let me mute the bottom one and play the top. And now let me mute the top and play the bottom. So they sound almost the same, but let's play them together now. So we'll unmute them. So now you can hear those beats, or those changes in the amplitude. Now let's calculate what the frequency of the beat should be. So frequency of the beat is going to be F1 minus F2. And so what were the two frequencies? Well, we had 440 and 444. And so if I put those two values in, what's my frequency of the beat going to be? It's simply going to be 4 hertz. So now let's check that with this model. And so what I'm going to do is now mix these two together, and we're making a single track of the two. And now let me get rid of those first two tracks. You can already see the beats. And now let's check our numbers. So let's look at 1 second in time. It's exactly 4 beats. The frequency of the beats equals the difference between the two frequencies. So did you learn to use a visual representation to explain how slightly different frequencies cause beats? I hope so, and I hope that was helpful.
All right. I hope that was helpful. I personally love these videos from Bozeman Science. It has like really great demonstrations and also super clear. And so if you're ever looking for any additional resources for your physics class, Bozeman Science is a great resource. Okay, so let's move on to our next slide. So the key points that you should have arrived, I'm gonna move my face over here, are to make sure that you write these key points in your notebooks. If you need to pause at the end of me reading them, then you can do that so you can copy them down. A forced vibration occurs when an object is made to vibrate. If a forced vibration of an object matches the natural frequency of an object, an increase in the amplitude of the vibration occurs. This is called resonance, right? And the resonance is exactly the reason why that glass shattered. Right? It was the pitch of the girl's voice was exactly the same as the pitch of the glass, or the resonance frequency of the glass. And then beats arise when two sounds of different frequencies are sounded together, resulting in a fluctuation of amplitude. The difference in the frequency of the two sounds tell us what the beat frequency is. Right? So this is different than the beats from like music is when you talk about like the beat dropping. This is a more technical definition of what a beat means. Okay, so for classwork today, you are going to complete the exit ticket that's on the bottom of your classwork document. Just a reminder, everything that you've done today, we did the reading, the video notes, and then complete the exit ticket. And make sure all of that is ready and uploaded by the end of today's class or by the end of today. Don't forget to hit submit on Google Classroom so we can count your work as submitted. The last thing that I wanted to share is the software that the person used in the last video, the Bozeman Science video. If you click on this link, it will take you to the tone generator that he used in the video. so that you can play around with it. That's just an optional thing for you to play. All the videos of all the links, including this frequency generator, are posted on the Simplicity of Science website for today's lesson. You can watch them again or show them to someone in your family, because I thought that video of her breaking the glass was actually pretty cool. Alrighty, I hope you all have a wonderful day, and see you tomorrow. Bye.